So this is a lecture about emergent collective behavior. And of course, this is one of the collective behaviors that everyone knows, the spontaneous formation of stop-and-go traffic. It doesn't seem to be difficult to drive in a circle. Drivers have all the information they need, they have a good education, a driver's license, they certainly want to avoid this phenomenon, but it happens still. So this is a result of systemic instability. In this case, an undesirable result of self-organization, and it can be understood in terms of mathematics. So there are models such as the intelligent driver model that describe the motion and the acceleration of vehicles in response to the distance and relative velocity of other vehicles. I won't go into all the details, but we can simulate all this in a computer and we can find different kinds of collective patterns of motion, different kinds of congestion that happen dependent on the circumstances. That means the flow on the freeway, the inflows through ramps, and all this. So it's quite astonishing that there's such a diverse zoo of different outcomes based on the same set of equations. And this is certainly not intended by the drivers, it happens by self-organization. And there is a systematic that can be put into a so-called phase diagram. In fact, you can see two over here, one for small perturbations on the left and one for large perturbations in the traffic flow on the right. That means the outcomes are dependent on the initial situation, the initial condition, and that means they're history dependent, right? So that is interesting too. But as you can see, basically, the flow situation determines the outcome. And this is a systematic for the behavior of human beings. In this case, sitting in cars, but they are in control, right? So the question is, can we do something similar also for other kinds of behaviors? And can we get rid of this undesirable self-organization? In fact, there is a possibility we can avoid congestion by so-called mechanism design, by changing the interactions between the cars. How to do that? You would need to equip the cars with sensors that measure the distances and relative velocities, and with a driver assistance system that would change the acceleration and deceleration behavior in response to the distance and relative velocity. And this can be done in a way, in fact, that would be able to overcome those annoying stop-and-go waves that we're seeing over here. So I'm just showing you this to illustrate that we can reproduce the experiment that we've seen before. We can understand the emergent traffic jams, and we can change the traffic jams to free traffic flow. You see that the problem comes from the cars that are entering the freeway. They're producing small perturbations. The perturbations are amplified, that causes stop-and-go traffic. Now, the traffic assistance system has been activated. That means the cars steer autonomously by themselves, and they're changing the acceleration, deceleration behavior, and this dissolves the traffic jam. We've done that in collaboration with Volkswagen at that time. In fact, the system was built into cars. Those cars were driving 10 years ago, in fact, before people were talking about Google self-driving cars. Those cars were making test drives in cities and on autobahns, and in fact it was working surprisingly well, I should say. Now, similar problems to congestion, which was an undesired outcome of the interactions of people, occur in social systems, such as, for example, tragedies of the commons. You see here the border between two countries. On one side of the border, there's forest. On the other side, of the border there's deforestation. So trees are gone, have been taken away to build furniture or just to burn it. So you can see in some cases there's a situation where there's environmental exploitation or environmental pollution and other kinds of social dilemmas. And it doesn't have to happen, however. It obviously depends on the circumstances, right? The legal framework, the social framework. So how can we overcome tragedies of the commons? What kind of framework, what kind of interaction mechanism does it take in order to avoid tragedies of the commons? Now, in the following, I will talk about the following subjects, all related to evolutionary game theory. This is just an overview. On the one hand, about the self-organized formation of behavioral conventions, such as the preference for the right-hand side, as we see it over here. What we also see is the self-organized formation of lanes of uniform walking direction. That means the different directions are automatically segregating, and that creates efficient patterns of motion, but also the preference for the right-hand side that comes on top of the self-organized phenomenon is another self-organized phenomenon that we'll discuss later on. And of course, it's a very exciting question: how can we reach social cooperation in circumstances where cooperation would usually not happen because it's unstable? Like the free traffic flow was unstable and something undesirable happened, that was the traffic jams. Now, we don't have to assume that people want to destroy the planet in order to explain why we have all these tragedies of the commons. The issue is cooperation would be desirable for everyone, but it's unstable, and that's why it erodes. And how can we avoid this erosion of cooperation? That's the question. And what kind of mechanisms does it take? What kind of framework does it take? And we'll discuss this. And we'll also discuss how moral behavior emerges. Humans are, most of them at least, moral beings. And so how does this come about? And why are we social? In fact, the most successful species on this planet are social species, measured in biomass. There's just one species that can compete with humans, which is ants. And ants are also social species. So, together we are strong. Together we can achieve things that a single human couldn't achieve. But how did we get to be social? Because there are so many species that aren't. And then, what causes social norms? And with this, I'm starting the main part of my lecture. So, Auguste Comte is often referred to as the father of sociology. And in fact, it was not called sociology by him in the beginning. He was using the term social physics because his vision was that it was possible to understand society as physicists were trying to understand nature. And obviously, understanding society is much more complicated than understanding that matter. And that's why he said, if we achieve this goal, then this is obviously the crown of science. The sociology would be the queen of sciences. That was his vision. Now, if you compare the success of different fields of science and you see how far we've come in sociology, then we're not quite there. But I will show you that we're on the way, in fact. I mean, there's quite a dramatic progress in terms of understanding social phenomena with mathematical models and by computer simulations. And the question is what approach to take. There are those who say we should describe things as detailed as possible. You know, like if you talk about trees, then the form of the trees and how the trees are branching and the form of the leaves and the color of the leaves and the reflections on the leaves and all these details, you know, certainly they matter in some way, but the question is, what do we want to understand? Physicists have always chosen this approach to say, let's use simple models with very few variables. Why? Because they're claiming like with 3 variables you can fit an elephant, and with 4 variables you can make him wiggle with his tail. You know, like basically, if you have a lot of variables, you can describe anything. It becomes a meaningless model, basically. You just need to change the parameter a little bit, this one or that one or that one, you will be able to fit it, right? So he's claiming, physics is claiming the less variables, the less parameters, I should be more precise, the less parameters you need to describe a phenomenon, the more powerful is the model. But there are also others that are trying really to reproduce every single detail of reality. And then simulating society would look like a 3D computer game, basically. And the question is, however, what can we learn from this? In fact, it turns out that this is done by the military, right? So the military is collecting a lot of personal data about you. Maybe you don't know this, but this is happening in order to create a digital double of yourself that will be simulated in their large war simulations, basically, right? A simulation of the entire planet. This is what they're doing, and so they're trying to collect more and more detailed data to reflect every single detail of the behavior that you've shown and make those digital doubles behave as similar as possible using machine learning. But it's a black box approach, right? And it might happen that tomorrow you bump into somebody, you know, say you stand in line of a cafe and take some time, you start talking to a person you didn't know before. You fall in love, you marry, you have kids, your life changes completely, you know, and all the computer simulations totally wrong. Now, if you happen to be somebody who becomes a politician or the leader of a business, you know, this one event, standing in line of that coffee shop, will change the world because your partner will influence your decisions, of course. Your family life will change your decisions, you know. So, from the point of view of complexity science, the situation is as follows. Systems can behave stable or unstable. They behave stable, then they can be pretty much understood by equilibrium kind of approaches. Details don't matter. And that's what you know. When you say, we can change much in the society, it means like, yeah, details don't matter. You can do this, you can do that, you know, you can go and demonstrate it. It won't change much, right? So you don't need all these details when society is stable. When society is unstable, however, something else happens. Maybe we need to shade. If society is unstable, then basically every single detail can make a difference. So no matter how many details your supercomputer knows about every single individual in the world, some random thing could really change everything. So then also, it doesn't really help. What we need to understand is what determines whether society is stable or unstable, whether it will go into a cooperative mode or into war, for example. And this is what we can understand with simple models.
About your graph there,
Yeah.
is that purely conceptual, or how could you derive the optimal?
Oh, the point is, the more parameters you have, the better you can fit a certain empirical data set, right? That's the descriptive power. However, parameters can only be determined with some accuracy, right? With some confidence. And so, if you make another measurement, a second data set that you don't use for calibration of your model, then the question is, how well can you predict the behavior in that second data set? And the more parameters you have, all uncertain to some degree, the higher is the chance that they will predict something that's not meaningful. And so the experience is, if you have too many parameters, then it doesn't help you to increase your predictive power, which again speaks against mass surveillance to do the world simulation, right? So here are a number of phenomena that from the point of view of sociology we'd like to understand. Homophily, that means why do similar people like to interact with each other and agglomerate? Social influence, collective decision-making behavior, cooperation in social dilemma situations, group identity, group formation, and all this. Social norms and conventions, conformity, integration, and so on. But also, on the other hand, social differentiation, inequality, segregation, diversity, social structure, such as hierarchical organization, or also flat networked organizations, deviance and crime, social exchange and conflict. And we'd like to simulate this based on a minimum set of assumptions, something that we wouldn't have to question, hopefully, such as births and deaths and the fact of reproduction of people. Individuals need resources. Many resources are material, that means limited, that creates competition. Competition implies fighting. Then there is tool-making ability, perception, curiosity as a matter of survival, memory, mobility, and so on. In fact, one can try to build these kind of models, but usually you would want to restrict to just a few ingredients, not all of them at the same time. And so we'll focus on those that are marked in red. And now we look into the issue of self-organized coordination and the emergence of cooperation. And I start with a short and incomplete history of socio-cultural evolution as I imagine it. So, cooperation problems really existed from the very beginning. People had to eat. They could hunt a rabbit, but they could also try to hunt a stag. A stag is maybe too big for a single person to successfully hunt, so you would have to cooperate, but then share the meat. Yeah, so basically there is a decision problem over here, and this is a social dilemma situation, and the question is, what happens in the end? Will people hunt rabbits individually, or will they cooperate to hunt stags? Another problem is the public goods problem, right? So certain things have to be done. Other people may benefit from doing it question is, will everyone help doing it? That means cooperate, or will some people profit from a few people doing that stuff? And free ride, basically. Exploit other people. Now, cooperation has been created historically in different ways. We know the institution of family clans, still powerful in some countries of the world, has also played a role, of course, in European history. So we're talking here about kin selection or genetic favoritism. That means you would give a favor to your relatives, basically, yeah? And that is something that can create cooperation, but the implication is that there would be conflicts between different tribes, between different families. Right? And as there are many families, basically, we couldn't live in peace. And those families would try to kill each other in order to have more resources. Then something new was invented. In the Bible, it's described. Something that doesn't depend on genes any longer, which is eye for an eye and tooth for a tooth. That means if you cooperate, I will cooperate too. If you cheat, I will punish you. So it won't pay off for you to cheat. Right? But it still creates war. We have even this institution of blood revenge in some countries, so we need something better. And so, yeah, here's a study on punishment by Ernst Fehr and Simon Gachter. And you can see, yeah, without punishment or other institutions, cooperation in social dilemma situations would disappear. You need to have an institution. Punishment is one of the institutions that does it. Yeah, and I said, this is also to create war, right? But some people claim actually war is the mother of civilization. You know, it's kind of spreading innovations throughout the world. I would be more careful, you know. I think it's making up reasons for war to justify it and present it as something good. There are other ways actually to spread great inventions and ideas throughout the world, and one of them is human migration. That has happened over thousands of years. People have always migrated, you know, it has always created stress also between populations, but altogether, I think they've learned from each other, and it helped their cultures evolve. Now, here's another point which really matters for people to form society successfully, which is you need to reduce aggression. If there's a competition for scarce resources, yeah, you might think maybe I should get rid of my competitors, you know, and kill them while they sleep and take their stuff that they've collected. And that was the situation early on, you know, when we had the situation where everyone was everyone else's wolf in a sense, right? So people really were not friends with each other, but it's really difficult to create society if people kill each other, and we know that there's some species of Homo that means of humans that died out, in fact, right? That couldn't reproduce quickly enough or didn't find enough resources in their environment. So becoming sufficiently peaceful that you can live together is a precondition to become social. In fact, we know from bacteria, for example, that they become more peaceful over time, one could say, because if they kill the host through a disease, it becomes more difficult to spread those bacteria. So, eventually those strains of bacteria that are less aggressive are more successful in spreading. Same thing with humans. So they obviously became more peaceful over time, and then they could live together, for example, in caves. They could start to do agriculture and farm and live in communities. Before, that wasn't possible. They had to go from one place to the next, basically. They were hunting until there were no more animals in the neighborhood. They had to go to the next place, but then you cannot accumulate stuff for the winter. If you cannot accumulate stuff, then it's very difficult to survive. So being able to live in one place for a longer time is a big step in the evolution of humanity, right? But in order to be able, you need to learn to cooperate, to farm, and to grow grain. But once you live in social agglomerations, you start to imitate other people's behavior. Find out, oh, this guy or that woman, found a trick to do something more successfully. And you would imitate this, right? In this way, knowledge spreads, and imitation is an efficient way of knowledge spreading, of learning. And that can be put into equations. This equation over here is basically describing how people are changing their behaviors or opinions when interacting with people who have different opinion or behavior. I prime. A is distinguishing different kind of subpopulations. And the W is the transition rate, basically describing the probability of changing from I to I prime. P is the relative proportion of people showing behavior I. So this is describing how that proportion is changing in time as a result of those interactions of people. And the transition rates have different terms. They could be spontaneous changes of behavior, they could be imitative changes, or you might say, I don't like this person, and that's why I won't imitate that behavior. I don't think this is relevant for me, and I would show some other kind of behavior. And if we now focus on the imitation only, that means set spontaneous transitions and avoidance behavior to zero, then we eventually get towards this equation over here, which is the replicator equation, known from evolutionary theory, how genes spread. This is an equation for how ideas or behaviors spread by imitation. So more successful ideas just have a higher spreading rate. Okay, and so this equation can be used to understand the spreading of behavior. We'll come back to this later on. So through imitation, people get more successful, agglomerations grow, people would start to cooperate with other people who have been friendly and supportive to them, so they would return the favors. That's called direct reciprocity, and eventually they're so efficient that not everyone has to farm, and they can differentiate. And that would be doctors, and there would be priests, and there would be people producing pottery, and so on. And trade can set in. So there would be exchange between different settlements, and would be further differentiation. So there would be an exchange of goods, And in the beginning, that's based on a barter economy. That means I give you some pottery, in return I get a bow from you to hunt, or something that I'm interested in. But I have to find somebody who has the kind of good that I'd like to have and who is interested in my goods. So that makes it kind of inefficient and very complicated trade relations at that time, and suddenly money was invented. So another good was added that was not needed in itself. That was just a proxy. So when I was buying something from you that I wanted to have, I just gave you money and said, you can take this money and get what you want from somebody else. So I don't have to go to 10 people to find the right person to settle this exchange, right? So that makes trade so much more efficient, right? Indirect reciprocity, and that also happens actually in social relationships. The Good Samaritan. You know, if I have to create cooperation based on the agreement that if I do this for you, you do that for me, we have maybe to talk for a long time. If we agree that we all are friendly to each other and help each other, then eventually this comes back to us, right? I help you, you help him, you help her, she helps me, or somebody else, you know. It's this makes all our lives better if we engage in indirect reciprocity. And eventually institutions like courts were established, and police, pool punishment is the key word, and schools and teaching and accumulation of scientific knowledge, and that's why we are here, right? Now let's get a bit more formal. The coordination problem. I was mentioning that pedestrians had this preference for one side, right? And now the point is if I and you are standing in front of each other and want to pass each other, we can each go either right or left. If I go right and you go right, we'll be successful in evading each other. If I go left, you go left, the same thing. Coordination has succeeded. If I go right and you go left, however, we will still stand in front of each other. We failed to evade each other. We'll have to make another attempt. We know this, you know, sometimes you have to do several steps in order to really avoid somebody successfully. Now, all this can be put into a payoff matrix, right? Doing the same thing pays off, so that creates a benefit. Doing different things doesn't pay off. That means there's a payoff of 0. And you can plug this payoff matrix into the replicator equation, and what you get is this equation over here. And you can look at the so-called stationary solutions where the proportions don't change anymore. So you set this to 0 and you find 3 solutions. P equals 1/2, P equals 1, and P equals 0. P equals 1/2 means we go to the right-hand side with 50% chance and to the left-hand side with 50% chance. It turns out that this is an inefficient and unstable solution. That means any small deviation from the 50-50 situation, that seems to be the natural solution to this game, will drive the system away towards one of the other stable solutions, where 100% will go to the right or 100% will go to the left. And this is what established a self-organized convention, right? People eventually learn that it's more efficient if everyone goes to the right or everyone goes to the left. So here it will be the right-hand side. In Japan, it's the left-hand side. So there's really evidence that this is happening through such a self-organization process. It doesn't matter whether it's right or left, it just matters that you coordinate. Now, you could also plug in different payoff matrices into the replicator equation. And one of the payoff matrices that people have been particularly interested in is the one of the prisoner's dilemma. Again, there are two choices. In this case, cooperate or not. It's called defection. And if both people cooperate, then they will get a large reward. But if one person cooperates, I cooperate, you don't, you get an even bigger payoff. I get a very small payoff called sucker's payoff, so I'm really bad off. And there's a temptation for you not to cooperate. So, say you won't cooperate, and I say, why should I then cooperate if you don't? And we'll end up in this state over here. Nobody cooperates, and that means a very low payoff for each of us. So even though it would be desirable for us, for each of us to cooperate, there is this temptation dynamic that leads us into a non-cooperative state, into this tragedy of the commons, right? And that's why some people think we should nudge people to do certain kind of things and steer their behavior, just control their thinking, basically, you know, called big nudging. But there's evidence that this is not going to work well either, and has serious side effects. Okay, now we're plugging in this payoff matrix that I mentioned before, and that T, R, P, and S, those payoffs vary, and then we get different kinds of games. The prisoner's dilemma, where cooperation is unstable and defection is stable, therefore cooperation is not expected to resolve. The harmony game, where it's just opposite, where cooperation is stable, defection is unstable, therefore cooperation always resolves. The second game, where both cooperation and defection are stable, and the outcome depends on the initial condition. How many people have cooperated initially? And the snowdrift game, where cooperation and defection are unstable, and a certain fraction of cooperation is stable. Right? So these are the different games, and in fact it's possible to turn the prisoner's dilemma into another game by changing the payoffs, for example, by introducing taxes. Right? That's why in Germany taxes are called Steuern. Of course, the government tries to steuern, that means to steer our behavior by changing the incentives, right? But that's a centralized way of changing the outcome. There are also decentralized way based on social interactions, and this is more interesting for us over here. So what are the mechanisms promoting cooperation? We already talked about genetic relatedness, about direct reciprocity, repeated interaction is needed for this. Reputation would create indirect cooperation based on indirect interactions. Clustering, formation of groups, for example. Also competition between groups, and I will talk here about a further mechanism that is migration. In fact, we have two legs, we are mobile, we can change our location, and that turns out to be quite important. Now back in 1992, Novak and May published a paper where they were simulating the interaction of people in a social dilemma game, prisoner's dilemma, but in a spatial setting. And they assumed not everyone would interact with everyone else, but they would interact just with their neighbors. And the surprise was that, in fact, not everyone ended up defecting. some cooperation survived. So neighborhood interactions can promote cooperation. That was an interesting finding, and that also means, in other words, the replicator equation doesn't describe these kind of situations correctly. They describe situations where everyone interacts with everyone else, or people interact with randomly chosen others. But here we have a structure, a spatial neighborhood relationship. Now, we have added this mechanism of success-driven motion. So we have assumed not all places are occupied by people. People can move to empty places. They would look in a certain environment around them and a certain radius and kind of check out those different empty places, which one looks promising, which has a nice neighborhood in a sense, right? If you're looking for a new apartment, you do exactly this basically. Try to get impression about the niceness of the environment. Now let's just look at this success-driven migration mechanism first. Assume there are two types of behavior, red and blue, and that you would change to a neighboring location if that promises to give you a higher payoff. And of course, the payoff matrix matters for the kind of behavior you will show, and also for the kind of interactions you have, and the patterns that result from this. Now, if you start with a situation where over this one-dimensional lattice, like from here to here, there are many different positions that you can be in, and we assume that people are equally distributed, the two types of people are equally distributed in all those different locations. So, flat distribution. You may think, well, that will stay like this forever. Not true. If there's some noise in the process, then what happens is that for certain kind of payoff matrices, this flat equal distribution will change. Like the fluid flow in the circle will change, and a pattern is formed. And these can be different patterns depending on the payoff matrix. There can be a segregation, which looks similar to the lane formation. There can be repulsive agglomeration, that means different types agglomerate in different areas, like different kinds of people live in different quarters of town, as we know. Zurichburg and Price here are quite different. Or there could be attractive agglomeration, right? Men and women are living together. So all of this is actually found in social systems. And now we'll combine that with change of behavior. I mean, people don't have a fixed behavior, but they can change it from cooperation to affection, or the other way around. And then what you find is there is an area where the initial equal distribution will be stable. I mean, no pattern is formed, but in most combinations of parameters, these are the payoff parameters P and S from the payoff matrix, there will be pattern formation. I mean, people change location and change behaviors, and there is a feedback effect between the two. And as a result, we find something very interesting. Now, if we simulate imitation only with 50% cooperators and 50% defectors, then what you can see is after some time, defection dominates, as we expected. Right? It's a social dilemma situation, and tragedy of the commons is expected to occur. If we have migration only, then 50% stay cooperative and 50% stay cooperative, that means there's no increase in the level of cooperation as well. Now, if we combine the two, we think there's no chance that this will increase cooperation, right? Because neither mechanism succeeded to increase cooperation. But it's not true. You find a dramatic level of cooperation. And that's based on co-evolution. Right? And it's a little bit similar to what we know from sociology, where people are shaped, people's behavior is shaped by their environment. You have a cooperative environment that makes you more cooperative. Now looks interesting, but I said, no, we can make that maybe even more interesting. Because reviewers were asking, but why wouldn't somebody spontaneously here in this cooperative area turn defective? And if you would do so, you could really earn a very high payoff by exploiting your neighbors. But only for a short time. For some time you could live like a Made in the Speck, yeah, as the Germans would say. You would, until people realize you're exploiting them, you could just exploit them, right? But, so there's a temptation. People would spontaneously turn into defectors. So we would have to add this, because here we don't assume any noise. So we have looked into different kind of noises. On the left, we have assumed that there's a certain probability where people spontaneously change their behavior. And they behave differently than predicted according to the payoff matrix and their neighborhood. On the right, we've assumed people would do spontaneous migration to other places, even though that's maybe not beneficial. Just sometimes, you decide to go on holiday and you stay there in another country. How many people are born in a different country? Let me see. It's probably the majority over here, right? So it all happened to you. Now, oh God, what happened now? So in that kind of situation, if you add these noises to the dynamics that we've discussed before, this dynamic. So both noises destroy cooperation. What do you think will happen? And the intuitive thing is cooperation will disappear, right? Even Ernst Fair said, I don't believe cooperation can exist if people would spontaneously be able to change their behavior. And then, yes?
But couldn't they still move away? If we still have the manipulation option, they could move away to another cooperation.
Absolutely. So basically what happens is when your neighbors start to cheat you, you would evade and you would stay in places that have a nice neighborhood, and when the neighborhood turns bad, you would go away. So you're one step ahead in a sense, right? In fact, we did a computer simulation starting with everyone defecting. A city of defectors, kind of hell on earth. But sometimes, spontaneously, somebody cooperated. Then, of course, that was not good for them, so they turned into defectors again. And for a long time, it was just defection. But then, after 25,000 iterations, a miracle happened. Because there were kind of 4 or 5 cooperators by coincidence in the same neighborhood. And so, for at least one of them, it started to pay off to cooperate. And cooperation spread by imitation. And within a very short time, cooperation spread all over the place, with a few exceptions. So there was an outbreak of cooperation, enabled by spontaneous mutations and migration. That was published in PNAS, and it was so incredible that, as I said, Ernst Fair couldn't believe it, and so we made an experiment in the lab. And we made it even more difficult because Ernst said, isn't that a green beard effect? If you do these test interactions with the neighborhood you would want to move to, and wouldn't you know beforehand it's a nice neighborhood? So basically the neighbors are revealing their behavior already to yourself. And I said, it's a good point, but I don't think this is going to change it completely. So we came up with an experiment where people couldn't see whether somebody was cooperative or not. They could just see whether there was somebody in a location or not. So they could move away from clusters of people, or they could move towards clusters of people. And that was enough, in fact, to stabilize cooperation. Without cooperation, without migration, cooperation disappeared, as you've also heard in previous lectures of this block course. But with migration, cooperation stabilized. And in fact, the average payoff increased with the level of cooperation. So there is a mechanism that allows cooperation to thrive if migration happens. So this is quite astonishing. Mobility is key to success, and that's why you're here. Yeah? Right. Shall we do that in the discussion session? Yeah.
Is somewhat a strange thing. There's three equilibria, and there are also three Pareto-optimal cells in this 2x2 game. So we chose the very special game, the limiting phase or the chipping game. Three equilibria. And I wonder if these results will hold for other games or more say, working model courses we usually use, like the prisoner's dilemma in other games also.
Now we use the prisoner's dilemma for those simulations.
So if you please, if you go back to this.
Yeah, I'd like to finish first and then make that part of the discussion, okay? So I'd like to finish basically with some studies about social preferences, because economists often say we are a homo economicus, I mean we're selfish, and if we weren't selfish we couldn't survive. Assume you're selfish and I'm not. The argument is that I would give you resources, you wouldn't give me resources. You would have more kids, I would have less kids, and so eventually you selfish guys would spread like hell, and the good guys would disappear. You know. That's what economists claim. I could never really fully believe it. And also there are so many experiments that question that, such as the ultimatum game and the dictator game, where people do share not everyone, but most people share all over the world a certain fraction of money, and even if it's not about money that the experimenter gives to people, like in this experiment that we did with Heike Rauhut, when this is about having to wait and to decide who would have to wait for how long, we still find the same kind of fairness preferences. And even under very anonymous conditions, I couldn't believe it myself. I thought if people don't know each other, if there's no chance that they would meet each other in the future, know that they've been cheated by that person or by that person, that would change everything, but that wasn't the case. And so the question is, why is this? And then many people say it's because people maximize individual utilities, not payoffs. Some people just love to cooperate because they feel good, but then it produces basically a circular conclusion. Because we would have to determine the utilities of every person empirically, and that's a hell lot of effort. And it wouldn't explain anything. So to have a good theory, we would have to be able to explain why you have this utility and you have that utility and so on. Otherwise, this utility theory is just useless. So we need a theory explaining moral behavior and individual fairness preferences. And that means we need to understand the evolution of Homo socialis. And this is the model that we have simulated. Agents decide according to a best response rule that strictly maximizes their utility function given the behaviors of their interaction partners around them, the neighbors. That's economic thinking, okay? They're selfish. The utility function considers not only the payoff, but gives a certain weight to the payoff of their interaction partners. But the weight, which is called the friendliness, is set to 0 in the beginning. That means everyone starts selfish, completely selfish, right? They could be friendly, but they start all selfish. Then friendliness is assumed to be a trait that's inherited, either genetically or by education, to offspring. And the likelihood to have an offspring increases exclusively with the own payoff, because you have to feed them, not the utility function. I mean, friendliness doesn't help you to feed your kids, in other words. It's assumed here, to have particularly difficult conditions in that simulation. The payoff is assumed to be 0 when a friendly agent is exploited by all neighbors. That means friendly agents like this would never have any offspring. They would just die out. And then there's one more rule. The inherent friendliness value tends to be that of the parent, but there is also a mutation rate. But to make it again difficult, we said it shouldn't promote friendliness, it shouldn't be a diffusion to friendliness, and that's how we specified the mutation rate. So the expected friendliness was 0.2, and what we later on find was average friendliness of 0.4, a much higher value. Now, if we modify where offspring grow up, in the neighborhood of their parents or somewhere else, then you find if they grow up somewhere else, then basically Homo economicus results. Economists are right in most of that parameter space. But there is a corner here where social preferences emerge. After many generations, like 50 or 100 generations, takes a long time. And this is when kids grow up in the neighborhood of their parents. As we do it. In fact, we're the only species where kids spend about 20 years with their parents. And that creates this social preferences that makes us social and makes us cooperative, that makes us more successful than other species. That means evolution has surprisingly made many of us other regarding. And here is how things change over time. So it really takes many generations until we have this sudden spreading of social preferences. And that's the distribution. In the beginning, everyone is assumed to be unfriendly, and then eventually we have this broad friendliness distribution with a significant amount of friendliness. And in fact, this fits reasonably well to experimental results by Ryan Murphy and others. They do find some selfish people, but most people actually have some degree of pro-social preferences, right? And actually even Adam Smith knew that. However selfish man may be supposed, he said, there are evidently some principles in his nature which interest him in the fortune of others and render their happiness necessary to him, though he derives nothing from it. And so even if we have different species, different families or different ethnicities or religions, whatever, you can see that based on the mechanism that I just discussed, eventually cooperation would emerge and spread, and also cooperation across different kinds of people. That means we can learn to have other regarding preferences also across genetic differences. We can learn to live in peace. And so we need a new model of man. Homo socialis is quite different from Homo economicus. If we would take independent decisions, then Homo economicus may sometimes be handled with standard economic metric methods, but interdependent decisions, when we care about others, of Homo socialis must always be treated with complexity signs. So that has quite some dramatic implications for our theoretical understanding of man and for the future of society. Thank you very much. So, coming back to the first question by Andreas, it's true that I think two parameters have been set equal and they've been set to 0 in order to make it easier to scan the parameter space, but I somehow remember we have also looked at that time into all sorts of variants of this, and also for a full person's dilemma where there are not two payoffs equal to each other, we would find this too. But of course not for all person's dilemma. If the temptation is too large, right, for example, then my creation can't compensate for this, right? If there's too much difference between some of these parameters, then my creation will have to be combined with other mechanisms such as the punishment of non-cooperative behavior, or with the creation of groups of similar level of cooperation, as Heinrich has certainly explained it to you, merit-based matching, and these kind of things, or reputation mechanisms. So there are several mechanisms that can promote cooperation, and depending on how large some patient is, you may have to combine several of those mechanisms.
I think we should know how much is dependent first on the structure of the game. You mentioned several games like Stefan, Lee, and so on. Then you chose a very limiting game, the case of a special game, the chip game. First thing is structure, and then within structure, how much is it dependent on a certain chosen set of
Yeah, we have done this. I mean, we have scanned, we have.
With these simulation models that you do not know is it really a feature of each special chosen situation. Same thing with behaviors experiments where one could show that its punishment ratio is larger than 3 to 1 or something like this. The results don't hold anymore.
Yeah, there's no universality in that sense, but we have certainly scanned parameter spaces and looked into variations of this. This model hasn't been shaped in such a way that it should produce this kind of outcome. For us, this outcome was quite surprising. The reason why we focused on this combination of payoffs is because a hell lot of scientific literature has done that before. It means basically most of the Nature and Science publications about spatial games looking into the prisoner's dilemma have used exactly the payoff matrix that we have used. So for a matter of comparison, to be able to compare our results with previous results, we've chosen to do that, but we've also looked into variations of parameters. As I said, if there's all the 4 payoffs are different, that's not in itself destroying the effect. It's, but of course, if there's too much temptation, then the force is too large to be compensated by migration alone.
I'm interested in the implications of your study about evolution of parents' preferences. Basically, as far as I can understand, that those regions grew up around the families with evolved these preferences, as those ones were actually the families gone. Now, does that mean that if we observe fair and altruistic behavior nowadays, is that then a remnant of some civilized past where we grew up, where we evolved in small groups, and it will disappear if we continue a civilization which is based on individualism? Or is it something,
I mean, there's certainly countering forces, like when kids grow up in families where they don't kind of, father is somewhere, mother grows up the kid, but mother has to work, kid goes to the kindergarten all the time. Hard to say how this would change the dynamics. We haven't simulated this. I mean, this is an abstracted model, of course. But we certainly can see that some kids that had kind of a difficult childhood and youth, they often have different character, different personality, and I would tend to say that this could actually undermine their social capacity.
let me put it differently. So the agents that evolve these preferences, if you introduce migration in that simulation, they would migrate to an area which those who don't have these preferences, they survive.
I mean, you're asking interesting questions, but I would have to hypothesize what's happening, you know, we can't just run the computer simulation over here. In principle, yeah, you could try to modify these kind of simulation models to try to reflect such kind of scenarios and see what happens, right? But I cannot answer it right now without doing such a simulation.
Sure, not only because you advocate migration so much that not so convention. So I was wondering if you combine this like this.
Yeah, my intention was not to say migration will heal the world or something. I focused on migration here because a lot of the other mechanisms that help to support cooperation have been already discussed with you in the previous lecture of the block course, right? And for us it was really a surprise. We did this kind of simulation only because before I did the traffic simulation, mobility was an area of interest, and I thought what happens if mobility comes together with these evolutionary gains. And I didn't see a reason why something special should happen, but we were just trying it out. And we were quite surprised that this co-evolution effect between spatial organization and behavior really has a dramatic implication for the level of sociality.
I have a question about your lab experiment on migration games. Could you say a bit more on what there's actually played in that game? So it was a prisoner's dilemma, as I saw, and it's like a chessboard. So 6 times 6 entries you have, and you can move there, and you have an environment, but people didn't know which game they actually played. Is that right? Or they didn't know.
No, they knew. I mean, it's already a few years back, so I have to memorize this hopefully correctly. I think it was either a prisoner's dilemma or more likely a public goods game that we played. And we probably had periodic boundary conditions. We had a certain range in which they could check out new locations, but they couldn't see the payoff that they would get beforehand, right? They could just see, is it empty or not? Are there neighbors or not? And what was the other question?
But then
So the game was
a new game
they
they
did-
were playing, but they couldn't see what the other players were doing.
right. They couldn't see it before, so basically it was a surprise action. But you could make the experience. If I'm staying close to clusters of people, this is good for me, or if I'm staying close to clusters of people, this is bad for me. And so you eventually learn being close or being away from others might pay off. You know. That's I think what happens eventually, that they make this conclusion that unfriendly people don't tend to live together, and friendly people tend to live together.
One last question,